بسم الله الرحمن الرحيم. Can you see my whole screen?
ايه
تمام. طيب last class, at the end of last class we stopped at this example اللي هو this is the that's the shift right register with parallel load and reset module, and in the slide there was a test bench that was created. The code is not here to show how this one will function, and we explained how it functions, and it went with expectation. ولكن we tried to implement it. If you remember, at the end of last class I wanted to show the difference between synchronous and asynchronous reset and how it affects the operation of any sequential circuit. So we took this code to EDA playground. We tried to do it and we had some error. Honestly, I don't know what was wrong before. I tried it again and it worked. I'm not sure why it didn't work last time. I even went back to the video to check the code. I didn't find any يعني ما لقيت أي فرق بين الكود اللي أنا كتبته الآن والكود اللي كتبته قبل. ف I don't know what went wrong. ولكن في شغلة كانت غلط اللي هي when in the declaration of shift register here هتلاحظ إنه البارامتر n مثلا الانبوت والاوتبوتس في طريقتين to declare it, either inside the brackets of the module او outside the brackets. بالنسبه للسيميليتر اللي انا بستخدمه رفض انه استخدم البارامتر n inside the brackets. بعد ما جربت الرن اعطاني ايرور انه no variable n was declared. ف what I did I just moved out this part اللي هو I defined the input or output outside just يعني like we normally do. تمام. and I defined parameter n before that and this code worked fine. هذا الفرق الوحيد بين الكود اللي امامكم الان والكود اللي قبل. كانت مشكلتنا اساسا في الكلوك الفوريفر. يعني اتذكر مسحنا كل الكود وخلينا الكلوك and it also didn't work. I'm not sure why, ولكن when I wrote this I didn't have any issues. تمام. So just a quick review. عندنا الموديول of shift register. We have reset signal and a load signal, and we have a serial n signal. This is a general code, so we will go with parameter n. For now it's declared as 8-bit shift right register. So at always at positive edge of clock, that means this is a positive edge triggered flip-flops, and at positive edge of reset, meaning this is an asynchronous active high reset signal. Inside the code, we check for reset. If reset is high, we're going to set Q to 0. Otherwise, we will check the load signal. If the load signal is 1, we will load Q with whatever we have at the input D. Else, if load is 0, that means shift right. So what we do here is we shift right the value of serial n. Serial n will be in um, in register Q0, and the rest of the register will take the value of the previous register. If you want the serial out, then we'll just assign the most significant bit of Q to serial out. Okay, this is the module. الآن بالنسبة للتست bench, I tried to recreate the same figure here. So that's what I did. First, I need to declare the input and the outputs. I usually use rig, ولكن for inputs you have to use rig. That's a must. For the output, you can use either wire or rig. That's all fine. And then I create an instance of my shift register. After that, I'll have two initial begin statement, one for generating the clock and the other to set the input signal. So for the clock signal, I'll set clock is equal to 1, and then each 5 nanosecond I will change the clock from clock to not clock. So it will alternate between 0 and 1 every 5 time units. Now why I did that, come back here to the figure. هتلاحظ انه الكلوك cycle from so check this clock cycle من هنا إلى هنا. This is one cycle. تمام. It goes from 10 nanosecond to 20 nanoseconds. تمام. معناته الكلوك سايكل is 10 nanosecond long. ولكن how much time is the clock spending at high and how much time clock spending at low? This is half the cycle. So this is 5 nanosecond and this is 5 nanosecond. So to create this exact clock, what I did is, if you come here, you see that my time scale is set to 1 nanosecond. So each time step is 1 nanosecond. And if you want a 10 nanosecond clock cycle, you need to change the clock every 5 nanosecond. تمام. So it will start at 1 for 5 nanosecond and then it will go to 0 for another 5 nanosecond. Now this is a complete cycle, and 5 plus 5, this is 5 nanosecond, this is 5 nanosecond, meaning my whole clock cycle TC is equal to 10 nanosecond. Okay, now that's the first part. Now we are done with this statement generating the clock. تمام. طبعا delay for 5 units, clock equal not clock, is inside a forever begin end statement. Okay, now I declare these signals just to recreate the same figure that we have in here. So I noticed that load went at 2 nanosecond for high and then went down at, I think, about 16 nanosecond low for the end of the cycle. Serial N was 2 nanosecond from beginning. It stayed on until 20, I think that was 26 nanosecond, stayed on for 10 nanosecond and then to 1 for the rest of the simulation. The value of D was set to 5A in hex up until 14 nanosecond and then was 0 for the rest of the cycle. So if you check this figure and you come back to the simulation, if I hit run, now this is exactly what we have. One thing, put this to binary. So this is the value of Q here, and this is the value of D. If you check this one and the one in the slide, it's going to be exactly the same. Okay, and you check the clock here, starting from 1 and alternating every 10 nanoseconds. Okay, now we already explained how this works and why these values are correct. Now what I want to do is to add the reset. So I'll add the reset around here تقريبا هذه 36 nanosecond. So let's do it at 38 nanosecond. I'll put the reset to high and we will check the difference between synchronous reset and asynchronous reset. Okay, so now this code is running on an asynchronous active high reset. So at the beginning of the simulation, I'll put reset equal to 0. So if reset equal to 0, this code should work the same as we saw before. So if you run it, check the signals, that's going to be exactly the same, no difference. Okay, now let's say at, where did I put it? Right here, I'll put reset equal to 1. So reset equal to 1 after how many? 2 and 14, that's 16, 26, 36, and then 38. So at 38 nanosecond, at t equal 38 nanosecond, reset will go to 1. Okay, so let's check what happens in the result. Okay, now this is the reset signal. Here, at t equal 38 nanosecond, I put the reset signal equal 1. Now check the value of Q. Just when reset went to 1, Q went to 0. تمام. Now this is an asynchronous reset. معناته reset when it gets active, it's gonna directly reset the circuit. Okay. Now check what happens when reset goes to 1, but this reset is a synchronous signal. So I need to delete the part where I say positive edge of reset in the sensitivity list of the module. معايا يا شباب؟
معك.
طيب now give it a
إيه
run.
معك يا دكتور.
Now what should happen when I run الآن؟ What we should expect to see إنه if reset 1 to 1 at the same time Q will equal to 0 at the next positive edge لأنه these statements will not be executed unless I get a positive edge of clock. I'm not depending on reset anymore. Give it a run. So at t equal 38 nanosecond reset 1 to 1 ولكن the value of Q was not affected. It's still equal to 6A in hex. When did Q went to 0? At the next positive edge of the clock here. Asynchronous reset لا. When this goes to 1 directly at exactly the same time this value should go to 0 at the same time. تمام؟ فهذا الفرق بين synchronous and asynchronous reset. Okay. And actually while I was working on that to get the exact times يعني it was a bit of a challenge. So probably I'll make one for you for the next homework. يعني أعطيكم timing diagram like this. Maybe I ask you to write the module or maybe I just give you the module وأعطيك a result of the timing diagram and I ask you to write this bench to regenerate exactly the same figure. تمام؟ all you need to do انك you يعني take care of the time. يعني مثلا let's check for the load signal here and see how I did it. الان اللود يعني here it's kind of hard to read ولكن at 2 nanosecond it was 0 at the beginning and then at 2 nanosecond it went high and then it went down at exactly 16 nanosecond. Okay, so how I did that in the test bench, at the beginning load is equal to 0 and then after 2 nanosecond طبعا why this is 2 nanosecond هذه المفروض 2 time unit ولكن it's exactly 2 nanosecond because I defined the time scale at 1 nanosecond. This is important to note. So after 2 nanosecond load went to 1 and then here at 16 nanosecond it went down. You cannot just simply write tick 16 time unit. No, because these are added together. هنا أنا already I waited for 2 nanosecond. To reach t equals 16, I need to go further for 14 nanoseconds. So that's why I put this as 14. So after 14 nanosecond, I put load equal to 0. Let's check it out. So for the load signal, I think, let me remove everything else. So here at 2 nanosecond, it went high, and then at 16 nanosecond, it went low. Sometimes you might get confused that this is the value of t. At t equal 14, do this and that. No, this is delay. Here, wait for 2 nanosecond, wait for 14 nanosecond, wait for 10, wait for an extra 10, wait for extra 2, and then I just put 82 here to make the simulation time to go 108, 200 nanosecond. Let's try. So 2 and 14 is 16, 16 and 20 is 36, 36 and 2 is 38, 38 and 82 is 120. Okay, so the total time is 120 nanosecond. I can ask you that as well. I can give you a code, a test bench code, and I ask you how long has the simulation يعني was running for. You just need to add this value, and you stop at the finish statement. Okay, so this is regarding the synchronous and asynchronous reset. Now let's continue on Unit 6. Today we should be talking about counters. So, counters. We already seen counters in Unit 2 when we talked about additional logic circuits. Some important logic circuit that were not covered in 212, we covered it in Unit 2. And one of those circuits is counters. طبعا counter is a sequential circuit, and simply what a counter is, it's gonna count from a certain number to a certain number depending on the number of bits and how you design your counter. Okay, so for example, a 3-bit counter should start from 000 and end with 111. After 111, it should go back to 000. And if you check the state diagram of a counter, it's gonna cycle between these values with no input. So every clock cycle, it will move from one state to the next state, and so on up until you reach the final value, which is 1111. And then this should go back to the first state. Okay. Usually, we have a reset signal for the counter. And of course, we must have a clock signal. Okay. Now you can design a counter just the normal way that you do for any sequential circuit. You start with a state table, or you start with a state diagram. From a state diagram, you go and build your state table after you decide on how many flip-flops you need. And then from state table, you come up with, you do your K-map minimization. After that, you come up with the equations, the next state equations and output equations if you have any output. And from that, you can just directly draw the circuit. Now, in Unit 2, we talked about two types of counters. Does anyone remember what are the types and what they mean? كان عندنا نوعين من الكاونترز.
سبيشال كاونترز ولا
لا السبيشال كاونترز اللي هي الجونسون كاونتر رينج كاونتر لا بتكلم from design perspective كان في two main types of counter like the way you connect the flip-flops to each other.
اتوقع ريبل كاونتر يا دكتور.
ايوه ريبل كاونتر والثاني
السينكرونس يا دكتور.
تمام سينكرونس كاونتر
طيب.
وريبل كاونتر. ايش الفرق بينهم؟ طيب to remind you the difference between these two counters كان عندنا ripple counter. الريبل counter let's say I have 3-bit counter. I take Q bar of Q0 if this is Q0, Q1 and Q2. I take Q bar of this output اللي هو Q0 bar and I connect it to the clock input of the next counter. And then I take Q1 bar and I connect it to the clock input of the next flip-flop. تمام. So this will work as a counter ولكن كان في مشكلة إنه going from 111 to 000 will incur huge delays because you have to wait for the signal to propagate to here and the signal to propagate to here. تمام. طبعا هذه this is the one that's connected to clock. This is ripple counter. بالنسبة للسynchronous counter لا. Synchronous counter, if I have a 3-bit synchronous counter, all of these clock signal will have a common clock. تمام. And I'll use extra logic to connect to the input of the flip-flops. So now this is, yeah, so what we usually do is we connect an incremental circuit here this incremental circuit will take the output as input of this incrementer, and this incrementer will just increase 1. So it's just an adder, a 3-bit adder. From the inside, the incrementer should look something like this. You have 3-bit of Q0, Q1, Q2, and here just connect 0, 0, 1. This output is going to D0, D1, D2. Okay, so each clock cycle you will get an increment by 1, and therefore it will result in a counter. So this is synchronous counter, and this is ripple counter. So what's showing here is a synchronous counter, and then an n-sized register containing a lot of flip-flops, or n flip-flops with a common clock signal. The output is connected to an adder, and the second input of the adder will be 1, so this will be my incrementer. So each clock cycle I get Q plus 1 here. Okay. Now in Verilog, that's extremely easy to do. Make your module counter, define your input. We have clock and reset, and we have an output reg Q. Now this is a code for a general n-bit counter. So I'll use parameter n, and I declare my output reg as from n minus 1 to 0. We already know that. So my always luck will have always at positive edge of clock and positive edge of reset, meaning I'm using an asynchronous active high reset. Always, if you have a reset signal, you must write this statement: if reset, and decide what you want to happen, what do you want to do if reset is equal, if reset is active. Now, reset is active at the positive edge. That means this is an active high reset. So if reset equal to 1, make Q equal 0. Else, this is where the counter is gonna work. So Q will take on the value of Q plus 1. ما في أسهل من كده. So that's a counter with an asynchronous reset. تمام. طبعا this code, this part, when you synthesize this circuit, is gonna create the same as this one. It will create this adder for you. It will put Q here, and it will set 1 for the second input. Now check the timing diagram. First, reset equal to 1. That means let the output be 0. When this goes down from here to here, the circuit is active because reset equal to 0 for the rest of the simulation. Now, reset went down here. Now the circuit is active. At the next positive edge, the counter will start working. So here it will read 1, next edge it will read 2, next edge 3, 4, and so on. This is that's an 8-bit counter, so it will go from 0, 0, 0, 0, 0, 0 up to all ones, which is FF. So from 0, 0 to FF, and then back to 0, 0 again. This is the same code, but it's not a general code. This is for a 4-bit counter. If you read this part, the output is declared from 3 to 0. That means this is 4-bit. Of course, we have a clock signal. Now here I have a reset n, and we said as a convention, n means an active low signal. And we'll also have a count enable signal. Okay, so how code will change? How our code will change. So at positive edge of clock or at negative edge of reset n, meaning asynchronous active low reset. Okay. Now inside, first thing to do, check for reset. If it's equal to 0, meaning our reset is active. So let Q equal to 0. If we don't have an enable signal, we can write else Q takes on the value of Q plus 1. But if we have a count enable signal, we only want to count if enable is equal to 1. So we'll change that to else if and will depend on the value of E. So else if E is equal to 1, count let Q equal to Q plus 1. Okay. So when you read a question about designing a counter, make sure that you read each and every word in the question, because there are so many variations. This is a code for 4-bit counter. That's your first clue, meaning Q will be declared from 3 to 0. If I change this number to 6, you make it Q from 5 to 0. An up counter. Up counter meaning it's incrementing the value of the output by 1. I can ask you for a down counter. If you have a down counter, what do you do?
-1.
-1. You just change this to Q will take on the value of Q minus 1. Okay, so second clue is this an up or down counter? With enable, that means you need to add one more control signal and asynchronous reset n. This should say, actually this should be an asynchronous active high, active low reset. Okay, or from this n, you can know that this is an active low reset signal. I can make this synchronous. هطلب منك synchronous reset n. So what you do, you come to this code, take off this part to make it synchronous, and then this is synchronous active low. ممكن اطلب منك synchronous active high. Active high meaning I will come here and I'll change this to 1. Okay, so every word matters. Read the whole question before writing your code. There are so many variations of designing counters. This also applies, by the way, to register, shift right, shift left. Make sure that you read the whole question one by one, and make sure you make notes on each word to make writing the code much easier for you.
يا دكتور
تفضل.
الانيبل مو مفروض اول شيء في الاف؟
لا. According to these slides, الانيبل هذه it seems to me انه I don't like to name it enable. What they mean by enable here is count. We did that before. كان عندنا one of the questions to design a counter with a signal called count. So if count equals 0, don't count. But you are allowed to load, you are allowed to reset. You can load and you can reset. If count equals 0, meaning don't count. If count equal 1, count. This signal that we used before اللي سميناها count is the same as enable in this set of slides. Okay. When I read the word enable, أنا عن نفسي أفهمها إنها enable the whole circuit. So all of this will be ignored, and first I will check E. For you, don't do that. Okay. Enable in these slides, meaning for a counter mean count. For the register also, it has a lower precedence than the reset and the load. I think we saw that when we talked about where did we see it? Enable
في الشيفت الظاهر.
Yeah. هذا register. This is not a shift. This is a code for a register with an asynchronous clear. Does it have a load? Yeah, of course, because it's a register. تمام. ف in this code you find enable has a lower precedence than reset. يعني first I will check for reset and then I'll check for enable. So I won't care about the value of enable if I'm resetting. تمام. I might think that enable will also disable reset. So if I want enable to disable reset, I'll first go with FE and then begin. Now I'll check for reset. So I'll say F reset, do such and such, else do such and such. So the difference between these two codes is that in this code, I'm taking enable to enable the whole, to enable all operations on the register. لكن هنا enable is only enabling the load. Okay. So to make it clear عشان لا أحد يتلخبط في الإكزام. When I say build an n-bit register with synchronous or asynchronous clear and enable, this enable is for the loading. It doesn't have to do anything with the reset. So a reset will have a higher precedence than enable. Okay. Same for the counter, as we see here. This enable means count. It's not enabling the whole chip. Okay. كان عندنا في الميموري, if you remember, we had a signal called CE, which is chip enable. This chip enable actually will disable all other signals. So if chip enable equals 0, the output of the memory will be disabled. هتكون كلها high impedance. If chip enable equal to 1, then just you can read the value of the address, read write bar, and whatever. Okay. طيب. Moving on, we will add one more signal for this counter. So this is a design of an up counter. That means Q is equal to Q plus 1. يعني أنصحكم يا شباب, when you read a question like that, while you read the question, try to make remarks for yourself so you don't make mistake while writing the code. So up counters mean Q equal to Q plus 1. Parallel load, that means Q is equal to D if L equal to 1. تمام. And enable, that means if enable, I'll either count or load. Is it? No, actually we said enable is count only. So if enable, count. Okay. طيب. Now let's check this code. The following is an implementation of a 4-bit up counter. So Q is declared as Q from 3 to 0. That has a parallel load input. That means I need to make an input called D, or whatever the input is. So D is also 4-bit. Using a selector L, this is your load signal, in addition to an asynchronous reset N. Once you see this, you know that your sensitivity list will have a positive or a negative edge of the clock, depending on the question, or a negative edge of reset N. And then enable input, we have enable E. The parallel data is provided as input vector R. So we read that, cancel this D and make it R. Okay, I just named it D here, ولكن he wants it to be R. Okay, so write your module. I have R, which is my parallel load input. I have reset N, clock for sure, E to count, to enable the count, L to load, and Q is my output. Now the input R should be declared at the same size as the output. So this is going to be input 3 to 0 R to make it 4-bit input. I have single input, which is reset N, clock, E and L, the control signals plus the clock. I'll have an output rig of Q. Now always remember to declare to write this value, because inside an always statement, if it's not a rig, it will give you an error. Okay, now write your code. Always add positive edge of clock. Add this if the reset is asynchronous. If it's active low, then declare as negative edge. So first check for the reset n. If not reset n, this is equivalent to if reset n is equal to 0. That's going to be the same. So if I'm resetting, Q is equal to 0. Else, check for the load. If I'm loading, then let Q equal to the input, which is R. Now, if I'm not resetting and I'm not loading, that means count, but I can only count if enable is equal to 1. Okay, so Q will take on the value of Q plus 1 if I have enable. الآن if reset equal to 1, that means don't reset. L is equal to 0, that means don't load. And E is equal to 0 means don't count. What's going to happen?
ولا شيء ولا
Nothing. So Q will equal to the old value of Q. Remember that these are flip-flops. So if you're not, like if all these values are not doing anything, means hold. Hold the value of the old Q. Okay. طيب, any questions so far? Okay. Moving on, we will do a down counter with parallel load. Down counter with parallel load. Do I have, does it have reset? No reset. Okay, so what I'm gonna do, I'm just gonna copy this code. Let me erase. المطلوب down counter with parallel load and enable. Okay, I have most of the information here. ما عندي reset, so let me take this out, take this out, and take this part out. Meaning, I'll also take this part out, and I'll keep this if. Now I have a parallel load, so when I go into the code, I'll check if I'm loading. If I'm loading, make Q takes on the value of R. Else, check for enable because I ask for enable. If E is equal to 1, I want to count down. So change this value to Q minus 1. If you do that, you will end up with this code. Okay. So this is also declared as a general code because it's using parameter n. All I need to do is you fix the value of the vector, the input vector and the output vector. So for a down counter, instead of adding 1, we'll just subtract 1.
دكتور
تفضل.
ممكن الاختبار يعطيني كود يقول لي صممه يعني أو رسمه؟
ممكن. So this will need your knowledge of this code plus whatever you learned in Unit 2. So in Unit 2 we designed all these counters. أعتقد الهومورك كان one of our homework, was it an incrementer or a decrementer? I don't remember. ولا ما أخذنا homework على counter. Wait. ما أخذنا homework على counter, بس كان في أسئلة عن كان في أسئلة في الكاونتر عن كان في أسئلة عن الكاونتر في التوتوريالز. تمام. So you should know how to design a counter. That's what I'm saying. So if you understand this code, you should be able to design the counter. Okay. it's not conventional ولكن يعني ما ادري اذا حيكون في سؤال بهذا الشكل او لا ولكن يعني it should be easy يعني to do not easy ولكن يعني you should know how to do it. Okay. All right. Moving on. Okay, so what if you want to make an up-down counter? Yeah, this was our question in the homework. We did that. We did have a question about counters. Now I remember. اعتقد
ايه صحيح.
اعطيتكم كاونتر ولا طلبت الكاونتر from scratch صح طلبت الكاونتر from scratch. So you designed the whole counter. تمام. And since you designed the whole counter, check how easy to do يعني how easy it is to do in Verilog. طيب. So for an up-down counter, meaning I need to add a signal to indicate do you want to count up or do you want to count down. So take the same signals from before. عندي load هذا input R for the load, clock of course, L to indicate if you want to load أو no, E which is count. We also had this signal in the homework. And then we have this extra signal called up down. Okay, and of course the output Q. So up down, if up down equal to 1, mean count up. If this signal is equal to 0, meaning count down. Okay, so let's check the code. I will declare the input R. This is for the parallel load. I have clock, load, enable, up down. This is the signal that we added from the previous code. My output reg. I don't have a reset, so at positive edge of clock, I will check if I'm loading. If you're loading, Q is equal to R. Now, else if you are counting, if count is equal to 1 or if enable is equal to 1, what do? You need to check the value of up down. So you can write Q takes on the value of Q plus, and then this one will create a multiplexer for you controlled by up down. And if up down equal to 1, route the value of 1. معناته I want this value plus 1. Oh no, it will become Q takes on the value of Q plus 1. هذا if up down equal to 1. If up down equal to 0, what do you want to do? You want Q takes on the value of Q minus 1, meaning you will route minus 1 to this counter. Oh, sorry, to this multiplexer. So this is when up down is equal to 0. Okay. So this is one way to do it. ولكن how for you, how would you write this part of the code if you were giving this question? How can we replace this to change it to write something else? So let's write it here, else if E. Okay. What do you think?
if statement ثانية للأب داون نفسها.
Yeah, you can do if up down. تمام. Q takes on the value of Q plus 1. Else else Q will takes on the value of Q minus 1. Okay. That's one way. You can use case statement. So you can write after the else if so else if E wait. Yeah. So else if count begin, I can write case up down. And 1 bit of 0 q takes on the value of q minus 1, and then 1 bit of 1, q takes on the value of q plus 1. And case, and for the else if. So you can, there are multiple ways to do it. Okay, we have 3 more counters to go, اللي هو ring counter, Johnson counter, and the linear feedback shift register. I think we should, I'll move this to next class because we spent some time on the code that we did last time. So beginning next week, we will have to take the tutorial class. So we'll have the morning class on Sunday and the tutorial class on the afternoon to make sure that we can cover, we can on Sunday we can start the modeling of finite state machine, which is the last section of this course. One more thing to note, I think I posted yesterday a homework for Unit 5. The deadline for this homework is next Tuesday before class time. Okay, so make sure you submit it before class time. Any questions?